March 8, 1945. The Rhine River at Remagen. Captain William Brehm of the 291st Engineer Combat Battalion stood in waist-deep water, watching American infantry sprint across the damaged Ludendorff Bridge while German artillery rounds walked toward his position. His hands worked automatically, securing anchor cables to steel pontoons, but his mind calculated a problem that would determine whether this bridgehead lived or died. The damaged railway bridge overhead, miracle that it was, couldn't hold much longer. When it collapsed, and Brehm knew it would collapse, every tank, every artillery piece, every supply truck for 6 divisions would need to cross on the pontoon bridges his battalion was building. Standard M2 pontoon bridges carried 40 tons maximum. The Sherman tanks waiting on the west bank weighed 30 tons. No problem. But intelligence reported something else was coming, something the engineers hadn't trained for. The new M26 Pershing, heavy tank, 42 tons, 2 tons over capacity. The German generals across the river had done the same mathematics. They'd watched American engineering operations for years. They knew Allied bridging doctrine, knew the weight limits, knew what American pontoons could and couldn't support. When Wehrmacht intelligence confirmed the first Pershing tanks had arrived in theatre, the calculation seemed simple. American pontoon bridges, built to 40-ton specifications, would collapse under Pershing's weight. Even if the Americans captured a Rhine bridge, even if they somehow held it, they couldn't reinforce with their heaviest armour. The river would do what German guns couldn't. Stop the American advance cold. They were wrong. What German planners didn't understand, what they couldn't have understood from studying doctrine and technical manuals, was that American combat engineers weren't following the doctrine anymore. They were rewriting it, in freezing water, under artillery fire, with math scribbled on waterproof notepads and solutions improvised from desperation and steel cable. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Rhine River had served as Germany's western defensive barrier since Roman legions first met Germanic tribes along its banks 2,000 years ago. 766 miles long, averaging 1,300 feet wide, swift and deep, the Rhine was no ordinary water obstacle. The U.S. Army Corps of Engineers declared it totally unfordable, even at low water. By early 1945, German engineers had pre-wired every significant bridge for demolition. Wehrmacht doctrine assumed, correctly, that destroying Rhine crossings would force the Allies into time-consuming amphibious assaults, buying weeks for German forces to regroup behind the river's protection. The calculations supported this strategy. A standard, American M2 treadway pontoon bridge, the workhorse of Allied river crossings, supported 40 short tons. That specification, class 40 inches military terminology, had governed Allied bridging operations across France, Belgium, and Western Germany. Engineers designed every crossing around it. Vehicles heavier than 40 tons required special bridging, which meant delay, which meant giving defenders time to range in artillery and prepare counterattacks. The M4 Sherman, America's primary tank since 1942, weighed exactly 30 tons. Perfect fit for standard bridging. British Churchill tanks, at 39 tons, came close to the limit but remained within specifications. Even the up-armoured Sherman Jumbo, at 42 tons, could cross if engineers doubled pontoon spacing. The system worked. From Sicily to Normandy to the Siegfried Line, American engineers had built hundreds of pontoon bridges and calculated every crossing the same way. Add up vehicle weights, compare to 40-ton capacity, space pontoons accordingly. But in January 1945, a new variable entered the equation. 20 M26 Pershing heavy tanks, shipped from the United States aboard the USS Sea Tiger, arrived at Antwerp, Belgium. These weren't Shermans. The Pershing carried a 90mm high-velocity gun capable of penetrating German Tiger armour at ranges exceeding 1,000 yards. It mounted 4 inches of frontal armour, nearly double the Sherman's protection. The trade-off was weight, lots of weight. The M26 Pershing, depending on configuration and ammunition load, weighed between 41.8 and 42 short tons. More than any existing American pontoon bridge was designed to carry. German intelligence noted the Pershing's arrival with considerable interest. Oberst Werner Osterkamp, Wehrmacht Chief Engineer for Army Group B defending the Rhine, received technical specifications from Abwehr agents who'd photographed American tank formations near the front. The numbers told a story. German defensive doctrine understood perfectly. American combat power, concentrated in armor, had just increased dramatically. But so had American vulnerability. Those 42-ton tanks couldn't cross on standard pontoon bridges. Simple physics. Too much weight, too little buoyancy, bridges sink. Osterkamp's report to Field Marshal Walter Model, commanding Army Group B, laid out the tactical implications. Quote, "Enemy heavy tank deployment will require specialized bridging equipment not currently in Allied forward units. Standard pontoon bridges observed at Ruhr and Moselle River crossings cannot support these vehicles. Intelligence suggests 3 to 5 days minimum to construct heavy bridging, during which forces east of Rhine remain unsupported by armor." Model circled the time estimate. 5 days. In March 1945, 5 days meant German forces could retreat, regroup, and prepare defensive positions in depth. 5 days meant American infantry crossing the Rhine would face panzers without tank support. The math favored defense. What Model and Osterkamp didn't know, because it wasn't in any technical manual or training document, was that American combat engineers had spent 3 years learning to break their own rules. Not recklessly, methodically. Every river crossing from North Africa to Normandy had taught the same lesson. Doctrine was a starting point. Reality was whatever you could build that wouldn't kill your own troops. And American engineers had gotten very, very good at building things doctrine said were impossible. The foundation of American bridging speed came from mass production and standardization that no German planner fully appreciated. By early 1945, U.S. factories had manufactured over 200 million board feet of Bailey Bridge components and more than 50,000 M2 pneumatic pontoons. Every single pontoon, whether built in Detroit, Pittsburgh, or Cleveland, measured exactly 4.8 meters long and 1.2 meters wide, every pontoon divided into 5 separate air chambers. Manufacturing tolerances meant any pontoon could connect to any other pontoon without adjustment or modification. If you knew how to build a bridge with pontoons from one factory, you knew how to build with pontoons from any factory. This interchangeability, boring on paper, proved revolutionary in practice. When the 1st Infantry Division captured German bridging equipment at Aachen in October 1944, American engineers incorporated captured pontoons into hybrid bridges the same afternoon, saved 6 hours of assembly time by using equipment already on site. German bridging systems, by contrast, required specific components manufactured to tight tolerances. Lose one critical part, the entire system became useless. American engineers didn't worry about losing parts. They worried about running out of parts, which almost never happened. The M2, pneumatic pontoon, standard equipment since 1942, represented elegant engineering. Each rubberized canvas boat displaced 2.8 cubic meters of water when fully inflated. Archimedes' principle, learned by every engineering student. A floating object displaces water equal to its weight. 2.8 cubic meters of water weighs 2.8 metric tons, roughly 3 short tons. One pontoon, properly inflated and anchored, could support 3 tons of vehicle weight before sinking below safe operating depth. For a 30-ton Sherman, engineers spaced 7 pontoons across a 30-meter bridge section. 7 pontoons, 3 tons each, 21 tons of support capacity for a 30-ton tank. Safety margin, 30%. Enough to handle wave action, current stress, and dynamic loading from moving vehicles. The mathematics changed completely for a 42-ton Pershing. 7 pontoons provided 21 tons of capacity, 42-ton tank. Math didn't work. Simply doubling pontoons to 14 would work, in theory, but 14 pontoons across 30 meters meant spacing them every 2.1 meters, too close. The pontoons would interfere with each other's buoyancy characteristics, creating turbulence that could capsize the bridge. Standard spacing called for pontoons at 4.5 meter intervals. Closer spacing required recalculation of every structural element, anchor cable angles, deck reinforcement, cross-bracing. The kind of engineering work that took trained specialists and slide rules and hours of calculation. Except American engineers at the Rhine didn't have hours. They had minutes. Lieutenant Colonel Harvey Fraser, commanding the 51st Engineer Combat Battalion at Remagen, understood the problem the moment he received word. Pershing tanks were en route to the bridgehead. His battalion had already constructed 3 tactical pontoon bridges across the Rhine, all built to standard Class 40 specifications. Beautiful bridges, technically. Clean anchor patterns, perfect pontoon spacing, textbook engineering, and absolutely inadequate for the tanks that mattered most. Fraser called his company commanders together in a requisitioned farmhouse on the West Bank. The meeting, recorded in the battalion's after-action report, lasted 17 minutes. No time for detailed analysis. Fraser sketched the problem on a chalkboard. Pershing, 42 tons. Standard bridge, 40 tons. Question: how do we fix this without tearing down existing bridges and starting over? Captain Edward Lamp, commanding Company B, had an answer that would never appear in any engineering manual. Don't fix the pontoons, fix the spacing. Reduce the distance between pontoons from 4.5 meters to 3 meters. More pontoons per bridge section meant more buoyancy per section, which meant higher weight capacity. Simple. Except spacing pontoons 3 meters apart violated everything engineers learned in training. The official manual, FM 5-475, specified 4.5 meters minimum spacing to prevent pontoon interference. Closer spacing, according to doctrine, created wake patterns that could resonate and flip the bridge. Lamp's response, recorded in his personal diary: doctrine assumes ideal conditions. This isn't ideal. This is the Rhine under artillery fire. We try it, or we tell tankers the new Pershings can't cross. I'm not telling tankers that. Fraser gave approval. Company B would construct an experimental bridge section using 3-meter spacing. If it held a Pershing's weight, they'd rebuild existing bridges overnight. If it failed, well, they'd figure out something else. American combat engineering in microcosm. Test it, fix it, do it again, do it faster. The challenge wasn't just spacing. Every modification to pontoon placement cascaded through the entire bridge system. Anchor cables, the underwater cables that prevented bridges from swinging downstream, in current, required recalculation. Standard doctrine used 25mm steel cables, rated for 15 tons of tension, angled at 45 degrees from the riverbed. 3-meter pontoon spacing changed the stress distribution across the bridge, which changed the optimal cable angle, which changed the required tension. Get the math wrong, and anchor cables would either snap under load or provide insufficient holding force, letting the bridge drift downstream into collision with adjacent bridges. Engineers at Remagen didn't have time to work out the trigonometry. They used an empirical method. Build it, load it, measure the drift, adjust the cables, try again. Trial and error, but fast trial and error. Bailey bridge decking, the roadway surface that carried vehicle weight, also needed modification. Standard Bailey panels, each 3 meters long and 1.5 meters tall, connected with steel pins through matching holes. The system's genius was modularity. Stack panels vertically to increase strength, place panels side by side to increase width. For Pershing crossings, engineers doubled the Bailey panels, creating what they termed a double-double configuration. 2 panels high, 2 panels wide. This quadrupled the deck's load-bearing capacity but doubled the weight, which meant even more pontoon support required. The calculations spiraled. Stronger deck needs more pontoons need tighter spacing. Tighter spacing needs stronger anchoring. Stronger anchoring needs heavier cables. Heavier cables need bigger trucks to transport them. Everything connected to everything else. Change one variable, recalculate the system. The Rhine's current speed at Remagen measured 2.8 meters per second in March 1945, swollen by alpine snowmelt. Fast water meant hydrodynamic forces that could tear a bridge apart if the engineering wasn't perfect. When a 42-ton tank moved across a floating bridge at 8 kilometers per hour, physics created something called dynamic amplification. The pontoons at the tank's position would dip deeper into the water, which created a bow wave that travelled along the bridge structure. If that wave's frequency matched the natural oscillation frequency of the pontoon spacing, the bridge would begin resonating like a suspension bridge in wind. Soviet engineers learned this catastrophically during the Dnieper River crossings in 1943, when improperly spaced pontoons created a harmonic wave that flipped an entire column of 34 tanks into the river. American engineers knew this danger. The solution wasn't eliminating the bow wave, which was impossible, but ensuring the wave's frequency didn't match the pontoon spacing. Mathematics, again. Wave frequency equals vehicle speed, divided by pontoon spacing. Change the spacing, change the frequency, prevent resonance. 3-meter spacing for Pershing crossings was deliberate. It moved the resonance frequency outside, the range of tank crossing speeds. But theory and practice, as combat engineers knew intimately, rarely matched. Especially when the theory came from textbooks and the practice happened in a river under German artillery fire. March 10, 1945. 48 hours after the Ludendorff Bridge's capture, Company B of the 51st Engineer Combat Battalion began constructing the experimental heavy bridge 200 meters downstream from the damaged railway span. Sergeant James Mitchell, a surveyor from Pittsburgh who'd built bridges across the Moselle, Ruhr, and Saar rivers, led the pontoon placement team. His crew worked in shifts, 2 hours in the water, 30 minutes warming by improvised fires on the bank, back in the water. The Rhine in March measured 7 degrees Celsius, cold enough to kill from hypothermia in under an hour without proper rotation. Mitchell's team inflated the first M2 pontoon using hand pumps, each man taking turns on the pump handles while others held the pontoon against the current. The inflation process, practiced countless times in training, took 12 minutes. Then came the critical part: positioning. The first pontoon had to be anchored exactly 3 meters from shore, aligned perpendicular to current flow within 2 degrees of tolerance. Any angle deviation would compound across the entire bridge length, potentially leaving the far side pontoons meters off target. Mitchell used a technique developed through trial and error at previous crossings: 2 upstream and 2 downstream anchor cables per pontoon, set at precisely calculated angles. The math came from experience, not manuals. 55-degree angles for upstream cables in current exceeding 2 meters per second. Worked at the Ruhr, worked at the Saar, should work at the Rhine. The second pontoon went in 3 meters from the first, then the third. By the time Company B positioned the 10th pontoon, German forward observers had spotted the construction. First artillery rounds arrived at 1400 hours. 105 mm shells, probably from German positions on the heights east of the river. The rounds landed 30 meters short, close enough to send geysers of Rhine water across the work crews, but not close enough to hit the bridge. Yet, German gunners were walking their fire toward the target, a standard adjustment technique. Next, salvo would be 20 meters short, then 10 meters, then direct hits. Captain Lamp, watching from shore, made a decision that violated every safety protocol in the engineer's handbook. Don't evacuate. Keep working. Stop now, and the German gunners get time to perfect their aim. Keep moving, keep building, and maybe finish before they find the range. Lamp's logic, recorded in the battalion's war diary. Artillery kills you whether you're working or hiding. At least working means we finish the bridge. The engineers stayed in the water. The 11th pontoon went in. The 12th. German. shells landed 20 meters short, exactly as predicted. The blast wave knocked 3 men off their feet, but the pontoons held position. 13th pontoon, 14th, 15 meters short now. Water spouts throwing Rhine spray high enough to soak the men working 50 meters from impact. 15th pontoon, secured with anchor cables that Sergeant Mitchell personally tested, pulling with his full body weight to verify tension. Satisfied, he signalled for the next pontoon. The 16th pontoon was being manoeuvred into position when German artillery found the range. The shell hit the riverbank 40 meters upstream from the worksite. Close enough. Shrapnel scythed across the water, punching holes in the inflated pontoons already in place. The multi-chamber design saved the bridge. Each M2 pontoon had 5 separate air compartments. Shrapnel punctured compartments 2 and 4 on pontoon number 8. Compartments 1, 3, and 5 remained inflated, keeping the pontoon buoyant. Reduced capacity, but functional. The engineers, training taking over, didn't pause. Can't stop for damaged pontoons. Note the damage, calculate the reduced capacity, adjust the spacing, keep building. Pontoon number 8 would support 2 tons instead of 3. Solution. Add an extra pontoon to the section to compensate. Change the math again, changed the spacing again, but kept the bridge functional. By 1600 hours, Company B had positioned 23 pontoons across 150 meters of the Rhine. German artillery continued firing, 10-minute intervals, but the gunners' accuracy decreased as smoke from American counter-battery fire obscured their observation posts. The engineers worked through it. They'd learned, over 3 years of combat, that you don't wait for safe conditions to build bridges. Safe conditions don't exist. You build bridges under whatever conditions exist and try not to die. The Bailey Bridge decking came next, the roadway panels that would carry vehicle weight. Each panel, 3 meters long, required 6 men to maneuver from shore onto the pontoons. In theory, teams lifted panels, carried them into position, dropped connecting pins through matching holes, moved to the next panel. Clean, efficient. In practice, working on floating pontoons in fast current, while wearing wet uniforms and trying not to drop 300-kilogram steel panels into the Rhine, nothing was clean or efficient. It was controlled chaos, 6 men shouting coordinates while the pontoons bobbed beneath their feet and the current tried to sweep the panels downstream. Private First Class Robert Chen, a welder from San Francisco, discovered the first critical problem at 1700 hours. The Bailey panels, designed for standard 4 1/2 meter pontoon spacing, didn't align properly with 3 meter spacing. The connection holes, drilled at precise intervals for standard bridges, were off by 40 centimeters. Too much for the connecting. Pins to bridge. Standard engineering solution. Stop work, recalculate, order new panels with different hole spacing, wait 3 weeks for manufacturing and delivery. Captain Lamp's solution, drill new holes. Chen and his welding team, working on shore with portable generators powering electric drills, modified 30 Bailey panels in 4 hours. They measured twice, drilled once, tested the connections by hanging their full body weight from the panels. Not elegant engineering. Not by the book, but it worked, which was the only standard that mattered. By 2100 hours, March 10th, the modified panels were being installed on the floating pontoon foundation. Each panel connected to the next with steel pins that dropped straight down through the newly drilled holes. The sound of sledgehammers driving pins echoed across the Rhine, metal on metal, building the bridge 1 connection at a time. The first complete span, 30 meters long, supported by 11 pontoons instead of the standard 7, was finished at 2300 hours. 10 hours from start to finish, including artillery interruptions, design modifications, and drilling new connection holes. Now came the moment that would prove whether American empirical engineering could beat German theoretical calculations. The test load. Captain Lamp requisitioned a Sherman tank from the 3rd Armoured Division, positioned on the west bank, 30 tons, within standard specifications. But this wasn't a standard bridge. 3 meter pontoon spacing, modified deck panels, anchor cables set at non-standard angles. Everything about this bridge violated doctrine. If doctrine was correct, the bridge would fail. If trial and error engineering was correct, the bridge would hold. The Sherman, commanded by Sergeant Paul Dietrich of the 32nd Armoured Regiment, moved onto the bridge at midnight. Slowly. 5 kilometers per hour, tracks grinding against the Bailey panel decking, the pontoons dipped under, the tank's weight, exactly as predicted. 8 inches of deflection at the quarter point, 12 inches at the midpoint. The bow wave, visible even in darkness, travelled ahead of the tank, causing pontoons to bob up and down in sequence. But no resonance, no harmonic oscillation. The wave frequency, dictated by the 3-meter spacing, stayed outside the danger range. The bridge held. The Sherman reached the far bank at 12:04 in the morning, March 11th. Captain Lamp watched it roll onto solid ground, then turned to his assembled company. Quote from the battalion war diary: "Gentlemen, we just rewrote the manual. Now let's build 5 more of these before the Pershings arrive." But building bridges for Pershings required more than just tighter pontoon spacing. The entire American engineering supply chain, built around Class 40 specifications, had to adapt on the fly. Lieutenant Colonel Fraser's biggest problem wasn't technical, it was logistical. Each heavy bridge required 40% more pontoons than a standard bridge. The 51st Engineer Combat Battalion's authorized equipment included enough pontoons for 3 standard bridges. Building 6 heavy bridges meant scrounging 1,400 additional pontoons from other units, from supply depots, from anywhere they could be found. Fraser sent requests up the command chain. 1st Army, 12th Army Group, eventually to Shea F headquarters itself. The message was simple. Remagen bridgehead has 6 divisions east of Rhine. Those divisions need heavy armor support. Heavy armor requires heavy bridges. Heavy bridges require more pontoons. Send pontoons or explain to Eisenhower why his bridgehead collapsed. Not from official supply channels, which would take weeks. From battlefield requisitioning, which took days. Engineer battalions across the entire Western Front, from Belgium to the Swiss border, stripped their equipment pools and sent pontoons to Remagen. Trucks, hauling pontoons, rolled through the night, convoys stretching for kilometers, all converging on the single most important river crossing in Europe. By March 13th, Fraser had enough material to build 8 heavy bridges. By March 15th, his engineers had built 6 of them, all operational, all carrying Class 50 loads, 50 short tons, 8 tons over the original specification, enough capacity to handle fully loaded Pershings with ammunition and fuel. The German response revealed how completely Wehrmacht intelligence had miscalculated American engineering capability. Oberst Osterkamp's initial report to Army Group B, dated March 10th, estimated 5 days minimum for Americans to construct heavy bridging. On March 11th, American engineers completed the first heavy bridge, 36 hours, not 5 days. Osterkamp revised his estimate on March 12th, 3 days, assuming Americans used specialized heavy pontoon battalions. On March 13th, he reported 6 heavy CAS bridges operational. His final report, dated March 14th, marked urgent and sent directly to Field Marshal Model, contained a single sentence: "Enemy engineering capabilities exceed all previous intelligence estimates." Model understood the implications immediately. American armor could now cross the Rhine in strength. Not just Shermans, Pershings. The 42-ton heavy tanks that could match German Panthers and Tigers gun for gun. The defensive advantage the Rhine was supposed to provide had evaporated in 1 week because American engineers had figured out how to build bridges German calculations said were impossible. Model's response, documented in Army Group B war diary, was prophetic. If American engineers can do this at Remagen, they can do it anywhere. The Rhine is no longer a barrier. It is merely a delay. He was right. Between March 7th and March 25th, American, British, and Canadian engineer battalions constructed 43 pontoon bridges across the Rhine. Most used standard Class 40 specifications, But 12 bridges, the ones built specifically for heavy armor crossings, used the modified 3-meter spacing developed at Remagen. Those 12 bridges carried every Pershing tank that crossed the Rhine in March 1945. Approximately 120 vehicles, each weighing 42 tons, each crossing on bridges that German engineering calculations said couldn't support them. The first M26 Pershing to cross the Rhine at Remagen was number USA 3066733, assigned to a company, 14th Tank Battalion, 9th Armored Division. The tank, nicknamed Eagle 7 by its crew, rolled onto Fraser's Bridge No. 4 at 0600 hours, March 16, 1945. The crossing took 4 minutes. The bridge, monitored by engineers with tension gauges on every anchor cable, never exceeded 80% of calculated capacity. Clean crossing, no structural stress. No drama, just a 42-ton tank crossing, a bridge that, according to pre-war engineering doctrine, should have collapsed. But the bridge held, because American engineers had learned that doctrine was guidelines, not limits. You could exceed the limits if you understood the math, tested the modifications, and were willing to work in freezing water under artillery fire until you got it right. German general officers, watching American armor pour across the Rhine, understood they'd been out-engineered. Not out-fought. Not outmaneuvered. Out-engineered. The Americans had solved, in days, a problem German staff planners thought would take weeks. And they'd done it not with revolutionary new technology, but with old technology used in new ways. Same pontoons, same Bailey panels, same anchor cables, just different spacing, different calculations, different willingness to question doctrine when doctrine didn't work. Field Marshal Albert Kesselring, who replaced Model as Western Front commander in late March, wrote in his post-war memoir, "The Americans demonstrated engineering flexibility we could not match. Our systems required precise conditions. Theirs required only determined men and enough material. When conditions changed, we recalculated. They improvised." By March 25, 1945, the Remagen bridgehead contained 125,000 American troops, more than 400 tanks, including 30 M26 Pershings, and over 20,000 vehicles of all types. All crossed on pontoon bridges built by combat engineers who'd rewritten the rules while German artillery tried to kill them. The bridges themselves, unglamorous and temporary, began to acquire nicknames. Fraser's Bridge No. 4, first to carry a Pershing, became Eagle Bridge. Bridge No. 7, longest of the heavy bridges at 210 meters, was Steinway Bridge, named after the piano company because engineers joked it looked like piano keys floating on water. Bridge No. 2, which took 3 direct artillery hits and remained operational, earned the name Lucky Bridge. None of these bridges appear in most histories of the Rhine crossing. The Ludendorff Bridge gets the attention because it was captured intact, dramatic moment that changed the timeline of the war. But the pontoon bridges, built afterward, mattered more strategically. The Ludendorff stood for 10 days before collapsing. The pontoon bridges stood for 2 months and carried the weight of an entire army. They were the unglamorous solution to an urgent problem, built by men who understood that engineering at war isn't about perfect solutions. It's about working solutions, delivered fast, under fire. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The mathematics that defeated German defensive calculations didn't come from textbooks or engineering schools. It came from sergeants with slide rules, corporals with waterproof notepads, and private first-class welders who understood that perfect calculations meant nothing if you couldn't build the bridge before German artillery killed you. The real innovation at Remagen wasn't technical, it was cultural. American combat engineers had developed, through 3 years of fighting across North Africa, Sicily, Italy, and France, an institutional comfort with improvisation that Wehrmacht engineering doctrine couldn't comprehend. German military engineering, excellent by any objective measure, operated within strict parameters defined by peacetime testing and theoretical calculations. When German bridge-building manuals specified pontoon spacing, they meant that spacing precisely. When doctrine called for specific cable angles, deviation wasn't permitted without approval from higher headquarters, which meant paperwork, which meant delay. This rigidity served Germany well during the war's early years, when Wehrmacht forces advanced so rapidly that engineering units barely had time to consolidate gains before moving forward. But in retreat, when every river became a defensive barrier and speed mattered more than perfection, German engineering doctrine became a liability. American engineers, by contrast, had learned flexibility from necessity. U.S. Army engineering schools taught doctrine, but combat taught adaptation. When 1st Armored Division engineers discovered that Tunisian sand didn't hold anchor stakes the way Virginia clay did, they learned to use wider stakes, driven deeper. When 7th Army engineers found that Italian river currents ran faster than training scenarios predicted, they learned to adjust cable tensions on site. Every crossing taught new lessons, and those lessons spread through the engineer battalions, not via updated manuals, but through personal communication. Sergeants who'd solved problems at one river taught their solutions to other battalions at the next river. By March 1945, American combat engineers operated with an informal knowledge base that no manual could capture. This decentralized learning system drove German intelligence analysts to distraction. Wehrmacht engineers could study captured American bridging equipment, which they did extensively. They could measure pontoon dimensions, test material strength, calculate load capacities. The equipment itself held no secrets. What German analysts couldn't study, because it didn't exist in physical form, was the accumulated practical knowledge that let American engineers modify equipment on site to meet conditions no one had anticipated. That knowledge lived in the minds of the engineers, passed sergeant to private, company to company, battalion to battalion, through the informal networks that form in any army that fights long enough. The engineers who built the heavy bridges at Remagen drew on solutions developed at a dozen previous rivers by men they'd never met. The 3-meter pontoon spacing wasn't invented at Remagen. It was refined there, tested there, proven there. But the basic concept, spacing pontoons closer than doctrine specified to increase load capacity, had been tried in experimental form at the Moselle in November 1944 by Captain Richard Morrison of the 33rd Engineer Combat Battalion. Morrison's bridge failed, pontoons too close together creating turbulence that nearly capsized the structure. But Morrison documented what didn't work, shared his findings with other engineer companies, and 6 different battalions experimented with variations over the next 4 months. By March 1945, when Captain Lamp needed to solve the Pershing weight problem, he wasn't starting from zero. He was building on months of collective trial and error. The German army had no equivalent system for rapid knowledge sharing across engineering units. German doctrine flowed top-down, from engineering schools to technical manuals to field implementation. Modifications to doctrine required approval from higher headquarters. Initiative was praised in theory, but constrained in practice by regulations that prioritized standardization over adaptation. This worked brilliantly in offensive operations, where German forces could choose their crossing points and prepare extensively. It worked poorly in defensive retreats, where river after river had to be crossed under pressure with whatever materials remained available. By March 1945, Wehrmacht engineer units were operating with equipment shortages, personnel losses, and disrupted supply chains that made by-the-book engineering impossible. But German doctrine provided no framework for off-the-book solutions. American doctrine did, not because it was written that way, but because American engineers had spent 3 years ignoring the parts of doctrine that didn't work. The human cost of this engineering race appeared in casualty statistics that most histories overlook: building bridges under fire, killed engineers at rates comparable to infantry assaults. At Remagen specifically, between March 7th and March 25th, U.S. Army engineer battalions suffered 347 casualties, 83 killed, 264 wounded. These numbers, recorded in First Army medical records, represented approximately 8% of the engineer strength committed to the bridgehead. For comparison, American infantry units during the same period suffered 12% casualties. Engineers died at 2/3 the rate of combat infantry, which would be remarkable, except engineers weren't supposed to be in combat. They were support troops, theoretically working behind the front lines. At Remagen, there was no behind the lines. The river was the front line, and engineers worked directly in it. Sergeant James Mitchell, the surveyor from Pittsburgh, who positioned the first pontoons for the experimental heavy bridge, was killed by German artillery on March 14th, while inspecting anchor cables on Bridge No. 6. The shell struck 30 meters from his position. Shrapnel severed his femoral artery. He bled out in the Rhine before medics could reach him. He was 32 years old, married, 2 children in Pittsburgh who would grow up knowing their father died building something most people never heard of. Private First Class Robert Chen, the welder who drill-modified Bailey panels to fit the 3-meter spacing, survived the war but lost 3 fingers on his left hand when a panel shifted during installation and crushed his hand against a pontoon. He was 20 years old. He'd been in combat for 7 months. Captain Edward Lamp, whose decision to use 3-meter spacing proved correct, was wounded twice, March 12th and March 19th, both times by artillery fragments. He refused evacuation both times, remaining with his company until the bridgehead expanded beyond German artillery range. His war diary, preserved at the National Archives, ends abruptly on March 22nd with a simple notation: Bridges holding. Mission complete. Request transfer to Paris for medical treatment. The request was approved. Lamp spent 6 weeks in hospital recovering from shrapnel wounds and exhaustion. These men weren't extraordinary soldiers. They were ordinary engineers doing extraordinary work under terrible conditions. What made them effective wasn't superhuman courage or exceptional skill. It was training, experience, and a command structure that trusted them to solve problems without waiting for permission. When Sergeant Mitchell needed to adjust anchor cable angles because current conditions didn't match doctrine, he adjusted them. No approval required. When Private Chen needed to modify bridge panels, he modified them. No engineering review board. When Captain Lamp decided to test 3-meter spacing despite manual specifications calling for 4½ meters, he tested it. His battalion commander, Lieutenant Colonel Fraser, didn't micromanage. Fraser set the objective, crossing requirement for heavy armor, and trusted his company commanders to achieve it however they thought best. This delegation of tactical decision-making to the lowest competent level was American military culture at its best. It enabled the kind of rapid adaptation that won Remagen. German engineering casualties at Remagen are harder to document because Wehrmacht records from March 1945 are fragmentary. What survives suggests German engineers suffered lower absolute casualties, but higher proportional losses. Pioneer Battalion, 53, responsible for demolishing bridges to delay American advance, lost 37 men killed and 82 wounded between March 1st and March 15th, approximately 40% of battalion strength. These casualties came not from building bridges but from failing to destroy them. The Ludendorff Bridge demolition, partially successful at best, cost German engineers 12 men killed when they were overrun by American infantry before they could detonate all charges. The bridge stood. The engineers died. Similar patterns repeated across the Rhine. German engineers, tasked with destroying infrastructure to buy time, kept dying in the attempt, while American engineers, tasked with building infrastructure to maintain momentum, kept succeeding. The strategic implications became clear to German commanders within days of Remagen's fall. General der Panzertruppen Hasso von Manteuffel, commanding 5th Panzer Army east of the Rhine, wrote in his March 16th situation report, "American engineering capability permits rapid exploitation of any crossing achieved. Previous assumptions regarding delay time for heavy bridging no longer valid. Recommend immediate withdrawal of armoured reserves from Rhine defence to secondary positions where river obstacles do not factor in defensive calculations." Translation: The Rhine doesn't stop Americans anymore. Pull back the panzers before they get trapped. Model ignored this recommendation, partially because Hitler had forbidden strategic withdrawals, and partially because Model still believed concentrated counterattacks could collapse the Remagen bridgehead. The result was exactly what Manteuffel predicted. German armour committed to Rhine defence found itself fighting American armour that had crossed on bridges. German intelligence said couldn't exist. The Panzerlehr Division, one of Wehrmacht's elite armoured formations, attacked the Remagen bridgehead on March 18th with 67 tanks. They faced the 2nd Armoured Division, which had crossed the Rhine on Bridge No. 4, the same bridge that carried the 1st Pershing. The battle lasted 9 hours. Panzerlehr withdrew, with 43 tanks destroyed or disabled. American losses: 11 tanks damaged, 3 destroyed. The difference wasn't tactical skill or fighting spirit. Both sides fought hard. The difference was, American armour had gotten across the river, while German armour had been held west of it, trying to prevent a crossing that had already happened. Engineering had determined the outcome before the shooting started. This pattern repeated across the entire Rhine front. On March 22nd, General George Patton's Third Army crossed the Rhine at Oppenheim, 60 miles south of Remagen. Patton, competitive by nature and desperate to cross before British Field Marshal Bernard Montgomery's meticulously planned Operation Plunder, drove his engineers to extraordinary speed. The 5th Infantry Division, spearheading Patton's crossing, established a bridgehead on the east bank using assault boats. Within 6 hours, engineers from the 86th Engineer Heavy Pontoon Battalion had constructed the first tactical bridge, 300 feet long, Class 40 capacity. 12 hours later, a second bridge stood beside it, this one built to modified Class 50 specifications using the 3-meter spacing developed at Remagen. The information had travelled. Fraser's engineers at Remagen documented their methods, transmitted the reports to 1st Army, which distributed them to 3rd Army, which passed them to the 86th Battalion. 7 days from innovation to implementation across 100 miles of front. Patton's tanks crossed on March 23rd. Montgomery's Operation Plunder launched March 24th. Patton had won the race, and he'd won it with bridges built using lessons learned 1 week earlier at a completely different river crossing. Montgomery's crossing, though later, was larger in scale and more thoroughly documented. Operation Plunder involved 25 engineer battalions, British, Canadian, and American, constructing 41 bridges across a 20-mile stretch of the Rhine near Wesel. Montgomery, cautious commander who planned extensively, had studied Remagen's results. British engineers built 14 bridges using standard Class 40 specifications. 7 bridges used modified Class 50 specifications. 3 bridges, designated for heaviest armour, used experimental Class 60 specifications that required pontoons spaced at 2.5 meters. This was pushing buoyancy mathematics to theoretical limits. British engineers tested the Class 60 design on March 20th using a Churchill tank loaded with concrete blocks to simulate 60 tons. The bridge held, barely. Deflection at mid-span reached 18 inches, close to the point where pontoons would submerge completely. But it held. On March 24th, when British Guards Armoured Division crossed with Churchill tanks, the bridges carried the weight. Doctrine said impossible. Testing said marginal. Practice said it worked. German defensive planning for the Rhine, developed over months by competent staff officers using reasonable assumptions, had failed completely. The failure wasn't tactical. Wehrmacht forces fought hard at every crossing. German artillery fired thousands of shells at American bridges. Luftwaffe jets, rare in March 1945 but still dangerous, bombed Remagen bridges repeatedly. German frogmen attempted underwater demolitions. Nothing worked. The bridges kept standing because American engineers built them faster than German forces could destroy them, repaired them faster than damage accumulated, and constructed redundant crossings so losing one bridge didn't matter. By March 25th, when the Remagen bridgehead expanded beyond German artillery range and the immediate crisis passed, Allied forces had established 14 separate bridgeheads across the Rhine. Combined, These bridgeheads contained over 300,000 troops, 1,500 tanks, and the logistical support for sustained operations deep into Germany. The Rhine, Germany's last natural defensive barrier, had been breached at multiple points simultaneously. The war in Western Europe was effectively over. Germany couldn't stop what was coming. The irony that would have frustrated German generals, if they'd had time to consider irony in March 1945, was that American success at the Rhine came not from revolutionary technology, but from evolutionary adaptation of existing technology. The M2 pontoon hadn't changed since 1942. Bailey bridges were British design from 1941. The innovations were in employment, not equipment. Spacing pontoons 3 meters apart instead of 4 1/2, doubling Bailey panels for heavy loads, drilling new connection holes in the field instead of ordering custom panels from factories. These weren't engineering breakthroughs. They were pragmatic modifications made by men who understood that doctrine was advice, not law, and that survival meant adapting faster than the enemy could respond. This cultural difference, American pragmatism versus German systematization, extended beyond engineering. German tactical doctrine throughout the war emphasized detailed planning and precise execution. Operations succeeded when conditions matched planning assumptions. When conditions changed, new plans had to be developed, which took time. American doctrine, particularly by late war, emphasized objective-focused planning with tactical flexibility. Operations succeeded when objectives were achieved, regardless of whether execution matched the plan. At Remagen, the objective was simple: get tanks across the Rhine. The plan, doctrine-compliant Class 40 bridges, didn't work for Pershing tanks. So, engineers changed the plan. Objective achieved. Mission success. German doctrine didn't permit this kind of mid-mission adaptation without higher approval. By the time German commanders recognized that Rhine defense assumptions were wrong and needed revision, American engineers had already built the bridges that made those assumptions irrelevant. The technical achievement at Remagen and subsequent Rhine crossings influenced U.S. Army engineering doctrine for decades. Post-war engineering manuals, revised in 1946 and 1947, incorporated the 3-meter spacing technique as an authorized method for heavy bridging. What had been field improvisation became official procedure. The classification system expanded beyond Class 40 to include Class 50, Class 60, and eventually Class 70 specifications, each with detailed instructions for pontoon spacing, anchor cable angles, and deck reinforcement. But the manuals also included, for the first time, explicit language authorizing field modifications when conditions required. Quote from FM 5-475, 1947 edition. Bridge commanders are authorized to modify standard configurations to meet tactical requirements, provided modifications are based on sound engineering principles and tested before full implementation. This was revolutionary. Pre-war doctrine had provided procedures to follow. Post-war doctrine provided increase to time, principles to apply. The difference mattered. Procedures worked when conditions matched training. Principles worked when conditions didn't. The engineers themselves, the men who built the Rhine bridges, mostly returned to civilian life after the war and rarely spoke about their experiences. This was common among combat veterans, but it was particularly true for engineers. What they'd done didn't fit popular narratives about heroism and combat. They hadn't stormed beaches or charged machine gun nests. They'd built bridges, unglamorous work, necessary work, deadly work, but not the kind of deadly work that made good stories. James Mitchell's widow received his posthumous Bronze Star at a ceremony in Pittsburgh in July 1945. The citation praised his exemplary courage and devotion to duty in the face of enemy fire. True, but incomplete. Mitchell hadn't charged an enemy position. He'd positioned pontoons in a river while being shelled. That kind of courage, the courage to keep working on a technical problem while people tried to kill you, didn't fit Hollywood's idea of warfare. So the engineers faded from popular memory, while the infantry and armour who crossed their bridges got the attention. But within the army, particularly within the Corps of Engineers, the Rhine crossings became legendary. Every engineer officer who attended Fort Belvoir's engineering school after 1945 learned the Remagen case study, the numbers, the mathematics, the problem-solving under pressure. What doctrine said couldn't be done. How engineers did it anyway. The lessons were technical but also cultural. Trust your NCOs, test your assumptions, adapt to conditions, build what works rather than what's theoretically perfect. These principles, learned in blood at the Rhine, shaped American military engineering through Korea, Vietnam, and into the present, modern U.S. Army bridging equipment, the improved ribbon bridge introduced in 1985, uses different technology, but the same principle. Modular components that can be configured in multiple ways to meet varying requirements. The IRB has no single, correct configuration. It has engineering parameters and mission requirements, and bridge commanders figure out how to match one to the other. That flexibility, that trust in junior leaders to make technical decisions without waiting for higher approval, traces directly back to March 1945, when sergeants at Remagen decided to ignore the manual and build bridges that worked. The German army learned similar lessons, but learned them too late. Post-war interviews with surviving Wehrmacht engineer officers, conducted by U.S. Army historians, reveal widespread recognition that German engineering doctrine had been too rigid. Oberst Werner Osterkamp, whose intelligence estimates about American bridging capability proved so wrong, survived the war and spent 2 years in Allied custody. In a 1947 interview, he acknowledged, "We understood American equipment. We studied their manuals. We calculated their capabilities based on doctrine. What we failed to understand was that Americans treated doctrine as guidance rather than requirement. This gave them flexibility we could not match with our systems." When asked what German engineers would have done differently, Osterkamp's response was telling. "We would have needed different training, different regulations, different command culture, not different equipment. The equipment we had was adequate. The system we used to employ it was not." By April 1945, the Rhine crossings were history, and Allied forces drove deep into Germany. The bridges remained, carrying supplies forward to support the advancing armies. Some bridges, built as temporary expedients to get tanks across one river, stood for months and carried millions of tons of supplies. Bridge No. 4 at Remagen, first to carry a Pershing, remained operational until July 1945, when the Corps of Engineers replaced it with a permanent fixed bridge. In those 4 months, Bridge No. 4 carried approximately 40,000 vehicles across the Rhine. Not bad for a bridge built in 10 hours by men working in freezing water under artillery fire using techniques that violated their training. The final tally of Rhine crossings between March 7th and April 1st, 1945, documented by Corps of Engineers records: 47 tactical pontoon bridges, 14 Bailey bridges on pontoon foundations, 6 fixed Bailey bridges, and miscellaneous ferries and rafts. These structures carried 7 armies across Germany's most significant river obstacle in less than 1 month. German defensive planning had assumed Rhine crossing would take weeks per army and require massive casualties. The reality was days per army, with casualties below pre-invasion estimates. The difference was engineering. Specifically, combat engineers who understood that their job wasn't following doctrine. Their job was accomplishing the mission. And if doctrine didn't work, they'd figure out something that did. The strategic impact extended beyond Germany's defeat. Soviet forces, advancing from the east, studied American Rhine crossing operations intensively. Soviet military doctrine, which emphasized rapid river crossings to maintain offensive momentum, incorporated American pontoon spacing techniques into Red Army engineering manuals. By 1946, Soviet engineers building bridges across the Vistula and Oder rivers in 1945 used spacing methods inspired by Remagen. The British Army, whose engineering doctrine had influenced American pre-war training, reversed the relationship post-war and adopted American flexible planning approaches. By 1950, most NATO armies trained their engineers using principles developed from Rhine crossing after-action reports. The tactical innovation that started with Captain Lamp's decision to try 3-meter spacing became, within 5 years, standard doctrine across the Western Alliance. Perhaps the most significant long-term impact was psychological. American engineers at the Rhine proved that technical problems that seemed impossible to solve quickly could be solved if you were willing to test, fail, learn, and try again under pressure. This lesson extended beyond military engineering. Post-war American industry, particularly in aerospace and computing, adopted similar rapid iteration development methods. Test the prototype. See what breaks, fix it, test again. This approach, chaotic compared to traditional engineering's emphasis on theoretical perfection before building, produced the jets, rockets, and computers that defined the Cold War. The cultural DNA was identical. Figure out what needs to work, build something, test it under realistic conditions, modify based on results, build it again. The engineers who built Rhine bridges in 1945 and the engineers who built lunar landers in 1969 operated with the same fundamental methodology. Define the objective, adapt to conditions, accept that first attempts might fail, learn from failure, succeed anyway. German engineering culture, by contrast, struggled to adapt this mindset. Post-war German industry, rebuilt with Marshall Plan assistance, produced excellent products using methodical design processes that prioritized theoretical analysis before prototyping. This worked brilliantly for many applications. German manufacturing quality became synonymous with precision and reliability. But rapid iteration development, the kind that accepts failure as part of the learning process, remained culturally difficult for German engineers trained in perfectionist traditions. When German computer industry tried to compete with American firms in the 1970s and 80s, the gap wasn't technical knowledge. German engineers understood computing. The gap was development methodology. American firms iterated faster, accepted more risk, learned from more failures, and got products to market quicker. The same cultural difference that let American engineers improvise Rhine bridges in 1945 let American computer engineers iterate software in 1985. Culture mattered more than capability. By 2025, 80 years after Remagen, the bridges were long gone, replaced by modern permanent spans built after the war. The Rhine flows as it always has, swift and cold, indifferent to the history that happened on its banks. No monuments mark where Bridge No. 4 stood, where the first Pershing crossed, where Sergeant Mitchell died positioning pontoons. The locations are documented in engineering archives but unmarked on the ground. This seems appropriate. The engineers who built those bridges weren't seeking monuments. They were solving problems, doing their jobs, trying to stay alive long enough to finish the mission. The mission was successful. The bridges worked. The war ended. That was enough. But the story matters because it reveals a truth about engineering and war that doctrine often obscures. Wars aren't won by the side with the best equipment or the most detailed plans. Wars are won by the side that adapts fastest when equipment fails and plans change. At the Rhine in March 1945, American engineers adapted faster than German defenders could respond. They built bridges doctrine said were impossible using methods manuals didn't include because they understood that reality trumps theory. When your 42-ton tanks need to cross a river and your bridges only support 40 tons, you have two choices: wait for better bridges or build better bridges. American engineers built better bridges. In 10 hours, under fire. Because waiting wasn't an option and doctrine wasn't an excuse. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.